Our next preliminary speaker is Dr. Simon Hollis. He is a lecturer in computer science at the University of Bristol. He undertook a PhD entitled Pulse-Based On-Chip Interconnect at the University of Cambridge Computer Laboratory. His research interests are in microelectronics, real estate design, security architectures. So I welcome Dr. Hollis.
And dinner and everything, so I'll make sure I don't overrun. And I'm wearing the fourth possible combination of outfit as well, so no jacket, but I have a tie, because I like my sense of ties. So, thank you very much for the very kind introduction, and I'm going to talk to you about, today, skipping the analysis. And, at first I have to say that this is work I couldn't have done without my PhD students, so the common theme between all of us talks today. So Chris Jackson has done a lot of the work in producing simulations behind this work here. So what do I mean by skipping the analysis? So we can go on to the first slide. Well, this work is all about saying, okay, we have systems coming out now that have an awful lot of processing ability. And they tend to be in the situation where you get multiple processing elements. And I don't really care whether you're talking about an FPGA here, or an ASIC which has 100 processors, or a graphics card which has thousands. But what you're seeing is that designs are coming out where you're getting many, many, many cores. And so these many core systems on chip are the same, with IP blocks being interconnected all over the place. And you have this shift in what's important. And previously, really, you optimized all of your logic paths, and you wanted to crank up the performance, even clock speeds, try and shift as much. Is really constrains performance in any kind of system. And the communication gives you what the overall execution time of the system is. It's not your worst case adder anymore, really. An awful lot of endless communication here. So move up here. So people have said, okay, now I have a communication problem, and it's not just that, it's also how on earth do I interconnect lots and lots of different processing blocks. And so here is a very skeletal picture of a multi-core system. And here are processors. And what people have done is said, okay, that's an awful lot, I'll copy it, I'll paste it the same design on the top. And it just tiles very nicely. So this mesh structure is very commonly used, and this is really what I'm going to revolve a lot of this talk around. So this is what the mesh NOC looks like. Next one. So you say, okay, now if I've got a system like this, how do I optimize for communication? And there's a lot of strategies you can use. The first one is, and perhaps the most common to date, is to say, okay, what I'm going to do is try and make sure that everything that wants to communicate is nicely near each other. So we'll call this the proximity mapping approach here. So if we flip to the next slide, then here's two processes. I can do that with many processors. But you can see there are lots of problems with this approach. One is that this is fragmentary. It doesn't necessarily, I can't necessarily fill the network neatly with lots of processes. It works for two here, but not for other ones. And also there's a dynamicism in the processors, so we slip on the next one. What we tend to do to get that kind of layout I just showed is a static analysis over the program. So you say, and then I try and do a fitting of my process, all the requirements, and the network I have, and make sure that everything can be placed where I want it. Now, this is unfortunately quite a bad idea right now, and it gets worse and worse and worse. Every generation of technology brings more and more complexities. And what's the fundamental reason behind this? Well, there's loads of reasons static analysis works really badly in parallel systems. The first one is that it's intractable for a large family of applications. Concurrent applications and non-deterministic applications really don't analyze very well statically. And it scales so badly because most of the algorithms that we know for this kind of mapping and also fitting algorithms are NP complete. So a lot of what you see at the moment in the literature is, here I have is a static mapping system, and I can deal with about 64 processors, but it takes about 3 minutes running on my high-end PC to be able to do that fitting. And ideally what you'd want is an embedded system to be able to do this fitting itself. Now ideally, here's the network you would want if these guys are communicating with us. One where instead of having these intermediate nodes, you have direct links. So if you could actually generate this form of network, you would get some way into sorting out the problem, because you no longer need to move or map any of these processes. The network actually essentially brings them closer topographically. So if we move on. And you can generalize that to say if you have any pairs of nodes in a network that communicate a lot, you would actually be an advantage if you can bring them topographically closer. And so there's this concept of a logical distance between two things. So without moving things rather than mapping the problem to fit the network. So you just turn it on its head. And it turns out this is more tractable than trying to go this way around. And essentially that comes because the network can observe the application, whereas the application writer can't observe the network, or often have to. So if we go this way, go next please. And so we'll end up with this idea called skipping nodes that aren't involved in thread communications to reduce the logical path, bring things closer together. But nothing actually would move. You'd put in 2 hop links here and 2 hop links here, that kind of thing. Okay, so what we want to know is whether our system, which now we provide no information from, that was pen and paper, the system when it runs, does it do anything? Does it do the right thing? So if you can flip to the other animation, what we're going to see is a complicated diagram. I want you to kind of clear your mind and wait for it to go white. Oh, white, there we are. Now what's happening is traffic is running, the darker is going to cycle. The darker the node, the more traffic is going through that node. And you see the links here, and these purple ones are the skip links. And this is running through time. So it'll start here, times 0. What happens is the system is evolving and placing these links where it thinks is a good idea. And not giving any information there, it's just observing the traffic running through the network. And these links are going and being inserted. Okay, and this is just a dump that we have, a diagnostic dump. So here, they grow in the corners, and they grow in the center here, and along here as time goes on. Okay, very flip back to the presentation. Next one, please. And so what I can do is I can now take that diagram and make it a lot simpler, and just look at it on here. And these numbers are now by time, where those links were placed dynamically by the network. And what do you see? Well, 1, 2, 3, and 4, they're in those corners we saw before. So if you go to the next slide, I think we have a side-by-side comparison. Here's where, with a static analysis,
Dr. Naik to come and present the memento.
Thank you very much.
All right, program out there at the poolside, and then we'll have dinner, and during dinner we'll have a dance program, which is authentic, local, regional dance. I wanted to repeat the earlier announcement we had made for the workshop for engineering scholars. We have this special category of admission where it is 1,500 rupees for people wanting to join, and please inform your those of you who are students and you want to inform your colleagues. That would be great. Thank you.